Welcome to this demonstration video. This is a piece of work that we're doing on behalf of the World Federation of Haemophilia. In particular, it's on behalf of the Laboratory Sciences Committee. My name's Steve Kitchen. I'm a laboratory scientist, currently a member of the Laboratory Sciences Committee. The chair of the committee is Dr. Sukesh Nair from Vellore, India. He's also had some input into this piece of work. We'll be demonstrating some methods and techniques that are described in some detail in our laboratory manual. I'm very pleased that this manual is available for free. It can be downloaded either as a single document, the full manual, or in fact in individual sections. We've set it up now on the website so that it's possible to select an individual method. So it's available on the World Federation of Haemophilia website. I think you know the address, www.wfh.org. And of course you also know that WFH is an international organisation, and so I'm also very pleased that we have available the manual in a number of different translations. It's available again through the website in Spanish, in French, Arabic, Russian and Chinese. So everything that we'll be talking about is described in some detail in the laboratory manual. So there are some important components of the inhibitor assay. Probably the single most important reagent is the source of factor VIII that we will use in the test. There have been a number of versions of the factor VIII inhibitor assay available to us for a number of years now, and historically the most widely used techniques have used plasma, pooled normal plasma, as a source of factor VIII. Historically, a number of centres used factor VIII concentrate, and if it's a concentrate that's used in the assay, then it's essentially an Oxford assay. Not widely used. The most frequent currently used assays employ plasma as a source of factor VIII. And in fact, the recommendations in the WFH Laboratory Manual, for example, and elsewhere, national guidelines, recommend use of pooled normal plasma as a source of factor VIII. For many years, the assay that was used was the conventional Bethesda assay, described originally in the mid-70s, Carol Casper and colleagues. And this was used for many years, but people became aware that there were some issues with this assay, and it's subsequently improved. And so the current recommendations from ISTH, SSC, and again also in the WFH Laboratory Manual, are to use a modification of the Bethesda assay. And the modification was described by colleagues in the Netherlands, in Nijmegen, and the name of the assay, Nijmegen modification of the Bethesda assay. So this is the recommended technique to use. So how does this differ? How is the Bethesda constructed, and what's in the Nijmegen modification? Both the Nijmegen and the original Bethesda, again, use pooled normal plasma as a source of factor VIII. The difference is that the Nijmegen modification recognised and described the importance of buffering the factor VIII. Buffering so that the factor VIII is protected. If we place plasma, including factor VIII, in a water bath at 37, we will progressively lose factor VIII over time from that plasma. It will happen by breakdown, by degradation, even in the absence of inhibitor or antibody. If we buffer the factor VIII, this protects the factor VIII better during that period so that the loss is much slower in the absence of added inhibitor or the presence of inhibitor. So if we don't have an inhibitor or antibody present, we still lose factor VIII, but that loss is much slower if we buffer the factor VIII to protect it. The detail of the Nijmegen modification, the technique for buffering, involves addition of a imidazole buffer to the plasma. And that's been carefully demonstrated in the publications. Actually, there are a number of ways to buffer pooled normal plasma, and it's highly likely that many of these other methods of buffering provide similar protection. And so I think the important thing is to use a plasma which has been buffered in some way. So if we incubate pooled normal plasma in a water bath at 37, there will be some minor loss of factor VIII. What we need to know in order to look for the presence of an antibody in a patient sample is whether or not adding that patient sample, with or without antibody, when we add that to pooled normal plasma and incubate in the water bath, do we see additional loss of factor VIII over and above the amount of factor VIII that would be lost simply by natural degradation? If we've got additional loss, it's caused by the presence of antibody inhibitor. And so this is the principle of the technique. We need some way to control for the loss of factor VIII over that incubation, since, as we've mentioned, there is some loss in the absence of antibody. So we need a control to control for this non-antibody related loss. So one of the important components of the assay is a control mixture. In the original Bethesda assay, the control mixture was an equal volume of pooled normal plasma mixed with assay buffer. Could be Auron's buffer, could be imidazole buffer, the buffer that's used in factor VIII assays. So 1 part pooled normal plasma, 1 part buffer. That's the original Bethesda. The Nijmegen modification also introduced a second change. First change, the pooled normal plasma is buffered. Second difference, second change, when that controlled mixture is constructed, it's a mixture of pooled normal plasma, not with buffer, but now instead with factor VIII deficient plasma. And you can imagine that this makes the control mixture more similar to the patient mixtures. Patient samples are not buffer, patient samples are very frequently severe haemophilia patient samples. So again, very similar to factor VIII deficient plasma. So we need a source of pooled normal plasma. And this can be, a number of materials can be used. Some centres prepare this locally as a pooled normal plasma, pooling citrated plasmas from healthy normal subjects, and that's acceptable. If this is done, then it's important to buffer this preparation for the reasons we've mentioned. We've got a method described in the laboratory manual, the WFH Laboratory Manual, in which that buffering is performed using a HEPES buffer. And the recipe and details are all, again, in the manual. I'd refer you to that. So that can be used. If that's prepared locally, then it can be stored in aliquots deep frozen. If so, it should be stored at an adequate temperature. -20 freezers, in particular domestic grade -20 freezers, absolutely unacceptable. Very frequently these will have automatic defrost cycles, the temperature of the plasma will raise, there'll be partial thawing, and this can really compromise the plasma that's stored in this way. So it's really important that the pooled normal plasma, if it's deep frozen, should be stored at a sufficiently low temperature. -35 will be adequate for at least 3 months, could be as much as 6. -50, -70, -80, then we'll get stability for at least 2 years, and of course that's an important advantage. We don't need to make the pool quite so frequently. So frozen local plasma is acceptable, it should be buffered. Many centres are currently using an alternative source of buffered normal plasma. Many centres use the pooled normal plasma that's available to them already commercially and being used in, for example, factor VIII assays. When we calibrate a factor VIII assay, we use a reference plasma. Very frequently, most frequently, a commercial material. It's been lyophilized, reconstituted for use, of course. But those commercial plasmas are also carefully buffered. Not usually buffered with the exact regime that's recommended in the Nijmegen modification, but nevertheless buffered for a similar reason, to protect the factor VIII, to introduce more stability once the sample is reconstituted. And again, many centres are using these successfully in factor VIII inhibitor assays. So I think there are a number of options. So we have, just now for the assay we're about to perform, some pooled normal plasma, buffered pooled normal plasma. In order to construct a control material, a control mix, we need a source also of factor VIII deficient plasma. And that can be, usually is, the same factor VIII deficient plasma which is used in factor VIII assays. However, there is an absolutely essential feature, and that is that we need to have a normal concentration of von Willebrand factor present in the factor VIII deficient plasma. There are a number of studies which have shown the results which we obtain in factor VIII inhibitor assays are influenced by the presence or absence of VWF in the factor VIII deficient plasma. So I think it's important that that's present in this particular setting. The other features that are important for the factor VIII deficient plasma would be the same ones relevant to a factor VIII assay. So in other words, it must be completely deficient in factor VIII, less than 1 international unit per deciliter, less than 0.01 international units per mil if you prefer. It should completely lack factor VIII. It's absolutely essential, of course, that it does not contain any inhibitor. We know that many factor VIII deficient plasmas, commercially available factor VIII deficient plasmas, many of these are constructed from normal plasma by immunodepletion. The manufacturer uses an anti-factor VIII antibody to remove factor VIII from normal plasma. This is a typical mechanism for creating factor VIII deficient plasma. And there have been reports that rarely the antibody used has found its way into the final material, so that the factor VIII deficient plasma contains some residual inhibitor. And this is completely inappropriate for use either in a factor VIII assay or what we're now discussing in a factor VIII inhibitor assay. I think that would be obvious. So should absolutely no inhibitor presence important. The other feature, of course, is the deficient plasma should contain normal concentrations of the other clotting factors relevant to a factor VIII assay. At the end, as you'll see, at the end of the inhibitor assay, we need to make a factor VIII assay. So the factor VIII deficient plasma, particularly there, should have normal concentrations of the other relevant clotting factors, contact factors, factor 12, 11, 9, 10, 5, prothrombin, fibrinogen. So that's the factor VIII deficient plasma. We have a test sample that we'll be using to demonstrate the assay. Just as for any other assay in hemostasis, we need some evidence. We need some evidence that the factor VIII, that the assay has been successful. And where do we get this? We get this most importantly from our quality control sample. It's really important to include a QC sample, a sample for which we know the level of inhibitor in advance. This should be included in the assay, and only if we obtain a result within our expected target, only if this occurs, can we safely release the test results for patient management purposes, just the same as for every other test. We did a survey of centres performing factor VIII inhibitor assays through one of our proficiency testing programs, and we noticed that a number of centres were not at that time including an IQC material, and I think that's a bad mistake in my opinion. It's absolutely essential to do so. So we have a QC sample. So we'll be preparing a series of mixtures, a control mixture, pooled normal plasma with factor VIII deficient plasma, an IQC mixture, the same pooled normal plasma with some of the IQC material, and some test plasma mixtures. Test plasma plus the same pooled normal plasma. So there are a number of things we need to think about when we are selecting and selecting dilutions to construct this assay. There are a number of things we need to keep in mind. In particular, we need to think, what is the level of inhibitor that we anticipate in the test sample? Sometimes we have some information that gives some clue about this. Often we don't. Sometimes when we're performing an VIII inhibitor assay, it's to confirm what we believe and anticipate that actually no antibody is present. Perhaps it's a screen as recommended in a number of guidelines. It's a check prior to important surgery, for example. So we may not expect to find an inhibitor in such a sample, but we need to confirm that it's not present. We may be monitoring a patient who we know to have an inhibitor in the past, perhaps a patient who's undergoing immune tolerance induction, or perhaps a patient where we want to check the level prior to a procedure in order to inform clinical decisions about which products should be considered. So sometimes we know some information in advance, and that we should take into account when we construct the assay. It will save us some time.